So far in this series, I've introduced the least action principle, which essentially states that all systems evolve according to the Euler-Lagrange equations of motion. And if you know the Lagrangian, you know the trajectory for all future times. Then I discussed the Noether theorem, which states that continuous symmetries of the Lagrangian, be they strict Lagrangian symmetries or action symmetries, generate conserved quantities called Noether charge. The familiar space-time symmetries imply conservation of energy and linear and angular momentum. My next topic is the Hamiltonian formulation of classical mechanics. But first, let's examine the Euler-Lagrange equations in more detail. Suppose we set the system up at time t equals 0 with the known position coordinates, q, and the known velocities, q dot. Suppose our time increment, k, is a really small number. What happens after our first time increment? Our position coordinate increments by this quantity, k times q dot. And if we know the new q dot at this new time point as well, then we can repeat the process and find q of 2 delta t, and so on for all future time points. But what is the new q dot going to be? The rate of change in q dot has to be q double dot. Euler-Lagrange tells us how to find it. If we go back to the matrix representation, we can solve for q double dot by bringing the alpha q dot across and inverting the W matrix, or the Hessian. Just as the Lagrangian is a function of q's and q dots, so is its partial with respect to any coordinate. So this thing here is basically a column vector of functions of q and q dot. And these n by n mixed second partials form n by n matrices. So this matrix is called the Hessian, and if it is invertible at every point q and q dot, the Euler-Lagrange equation gives us q double dot, the increment in q dot between successive infinitesimal time steps in terms of q and q dot. In other words, our system is a point in position velocity space. If we know where we are, this time evolution vector field tells us which way we're heading. The change in the q is just q dot. The change in q dot is the inverse Hessian times f minus alpha v. If we know where we start, we just follow the flow. And so we can answer everything and anything we ever want to know about the system. A one-coordinate system has a two-dimensional position velocity space. Two-coordinate system has four-dimensional QV space, which is hard to draw on a computer screen. You need 6 numbers, 6 dimensions, to completely describe a three-coordinate system. So it's difficult for us three-dimensional beings to visualize a 6-dimensional space. So I'm going to illustrate a lot of these concepts with a 2D space, just a simplified system that only has one coordinate. The Hamiltonian formulation of classical mechanics is just a coordinate transformation. We keep the q's, but we replace q dot with these new numbers called canonical momenta, p. So if you remember from the beginning, we said we define the canonical momentum conjugate to q as dl dq dot. This is normally a function of one or more q's and q dots. So, if we define these new variables, how do we get rid of q dot? We want to make q dot the subject, so we can substitute everywhere to get rid of it, and have all our equations in terms of p and q. This is the tricky step in switching from the Lagrangian to the Hamiltonian, and I want to come back to this issue at the end of the video series when I talk about situations where this is impossible. Unless this transformation is degenerate, it should at least in theory be possible to do this transformation. Whether there exists an analytical expression for this function, that's irrelevant, because when it actually comes to solving these equations in practicality, they're going to be approximations in one way or another. So we know how our position velocity coordinates evolve, but how do these position momentum or phase space coordinates evolve? Well, this equation doesn't change, except q dot is now some function of p's and q's. But we need to know how p will change. The Euler-Lagrange equation explicitly stipulates that dl dq equals a total derivative of p. Remember, this partial is the change in L as q changes, keeping the velocity fixed. Why do we bother with this coordinate change? One reason is that it's easier to see q and p on an even footing in the Hamiltonian formulation. The Lagrangian evolution of q and q dot look very different from each other, but would you believe there exists a special function of q and p such that q dot is just dh dp, keeping q fixed, and p dot is just negative dh dq, keeping p fixed. What is h? Well, if we know q dot as a function of p's and q's, then h is just p q dot minus the Lagrangian, where we sub out the q dot everywhere in terms of p and q. Let's just check this. The partial with p holding q constant gives us the q dot function plus this other term. But the Lagrangian has dependency through q dot, so by the chain rule we'll get a term dl dq dot times dq dot dp that exactly cancels out with this p dq dot dp term. So they cancel out. What about this equation? Both terms have dependency on q through its q dot, and these two terms cancel exactly, leaving just dl dq as required. To recapitulate, this process, the Legendre transformation, takes a Lagrangian, a function of q dot, and defines a new variable, p, as its derivative. Within some range, p is 1 to 1 with q dot, so we can invert these relationships and express L in terms of p. We can also add q dot p and a minus sign, and suddenly we have a function that expresses the Euler-Lagrange equations in this beautiful, symmetrical way. These are called the Hamiltonian equations. We will meet the Legendre transformation again when we do statistical physics and thermodynamics. The transformation is special because we can reverse it by repeating it. For example, if we take this Hamiltonian and define a new variable, dh dp, what is dh dp? By construction, that's the same as our old variable, q dot. So the transformation tells us that to change p's back to our original variable, we have p q dot in terms of q dot minus this same quantity plus our original Lagrangian in terms of q dot. So this beautiful duality connects quantities such as energy and enthalpy and Helmholtz and Gibbs free energy, but that's another story for thermodynamics. Okay, suppose we have some quantity A that depends on our system variables Q and or P. If we know the Hamiltonian, these Hamiltonian equations tell us Q and P as a function of time, and so we know A is a function of time. If we want to know how A changes over time, we just need to use the chain rule. A dot equals dA dq times Q dot plus dA dP times P dot for each Q and P. Remember, the Einstein summation convention applies here, as always. But these derivatives are just dH dP and negative dH dq respectively. And this expression has a special name. It's called the Poisson bracket. When you take two functions, A and H in this case, of Q's and P's. For each conjugate pair, you multiply these derivatives and then you add. And then write a minus sign and you switch the roles of the Q's and P's. We can rewrite the Poisson bracket in matrix form, where the I index represents a whole row of Q and P derivatives, all 2n of them, and likewise this 2n column vector. The matrix in the middle, called the symplectic matrix, is a 2n by 2n matrix where the zeros and ones represent the zero and identity matrices respectively, and it switches the order around so that the 2n column of position and momentum derivatives becomes a string of momentum derivatives, then a string of negative position derivatives. So to multiply with a row matrix gives a dot product where the first n terms are momentum derivatives times position derivatives with a minus sign, and the other n terms are position derivatives times the momentum derivatives with a plus sign, which is exactly how we defined the Poisson bracket in the first place. The Poisson bracket starts with two functions of phase space variables, and it spits out one function of phase space variables. If one function is a linear combination, the answer is also a linear combination. If you reverse the order, you get the same quantity with the minus sign. If you want to Poisson a function with a product, then the product rule gives you these two terms, and that's called the Leibniz property. Finally, we have the Jacobi identity. Let's say you find this Poisson bracket, then Poisson it with another function, a. This is what you get. Now imagine the functions a and c swap places, and you subtract. In other words, we are now calculating this quantity. What does it equal? When a and c swap places, this term cancels with its counterpart, its identical counterpart. So they cancel out. On the other hand, these equivalent terms don't quite cancel, but instead form a Poisson bracket between a and c times the mixed partial. Likewise, this term cancels with its identical counterpart, while this one forms a Poisson bracket with its twin. Okay, but the CA bracket cancels with the AC bracket. So really we're just left with these four terms. Now let's collect the terms with dB dQ and the terms with dB dP separately. And suddenly these look like the P and Q derivatives of the AC bracket. In other words, the difference between these two nestled commutator brackets is itself a nestled bracket, and we rewrite the Jacobi identity in this way. Alright, if you have a bilinear antisymmetric closed binary operation that satisfies both the Jacobi and Leibniz identities, this is called a Lie bracket. A Lie bracket, L-I-E. There are a couple of other examples of Lie brackets in physics, and at the end of this video series I will mention Dirac brackets. In my next video series on quantum mechanics, I'm going to talk about commutator brackets and Moyal brackets. Okay, that's all for now. I'll see you in the next video.